All right, welcome to the Explainer. Today we are opening up the engineer's toolbox. We're going to take a look at some of the tiny, really specialized components that are the true unsung heroes of our modern world. I mean, they're in everything, from the phone in your hand to the power grid that lights up your city.
It sounds like a trick question, right? But the answer is actually pretty simple and, honestly, kind of fascinating. Both of these devices rely on little tiny electronic parts that act as their brains, controlling power, or sensing the world around them in some surprisingly clever ways.
So before we can get into all the really specialized stuff, we have to start with the foundation. We need to understand the absolute cornerstone of all modern electronics, the bipolar junction transistor, or BJT for short. Just think of this as the original fundamental building block that pretty much kicked off the entire digital revolution.
The name itself is actually a hint about what it does. Its original name was transfer resistor because it literally transfers a signal from a low-resistance part of a circuit to a high-resistance part. They just squished that down to transistor. And that very act of transferring is the secret sauce behind how it amplifies a signal.
Now, BJTs come in two main flavors, if you will, NPN and PNP. And as you can see, they're basically a little sandwich made of 3 layers of different semiconductor materials. It's the specific order of these layers that completely dictates how the transistor is going to act in a circuit.
The easiest way to picture this is to think of a water faucet. The base terminal is the handle you turn. It takes just a tiny little bit of effort, a tiny bit of current, to turn that handle, but that small action controls a huge, powerful flow of water, or in this case, a much larger current between the other 2 terminals, the collector and the emitter, and that right there is amplification.
And here's what makes the BJT so incredibly versatile. Just look at this. Depending on how an engineer wires up those 3 terminals, this single component can do totally different jobs. It can be used for boosting high-frequency radio signals, or it can be the thing that drives the speakers in your phone. It's like an electronic Swiss Army knife.
Okay, so the transistor is fantastic for small signals, but what happens when you need to control some serious, massive amounts of power? We're talking about the kind of electricity that runs a giant industrial motor, or even just the main power coming into your house. For that job, you're going to need a bigger hammer.
Well, for that, we need to turn to a totally different, more robust family of components called thyristors. These are the real heavy lifters of the electronics world. They are designed for one thing and one thing only: power control.
And the undisputed workhorse of this family is the silicon-controlled rectifier, or SCR. Now notice it has a 4-layer structure, PN-PN. That's one more layer than the BJT we just looked at. And that extra layer, that is the absolute key to its unique power handling skills.
What's really clever is how an SCR actually works. You can think of it as 2 transistors that are connected together in a special kind of loop. When just a small pulse of current hits its gate, it triggers this internal loop and the whole thing latches on. And it stays on, conducting full power until you cut the main power completely. It's like a switch that locks itself in the on position.
Now, other thyristors are built to handle the alternating current, or AC, that you get from a wall socket. Both the diac and the triac can handle current flowing in 2 directions. The big difference, though, is how you turn them on. A diac is kind of dumb. It just turns on by itself when the voltage gets high enough. But a triac gives you precise control with that gate terminal.
And this brings us full circle. Remember that lamp dimmer we talked about? This is the guy doing all the work inside, the triac. The dimmer circuit uses that gate terminal to send out perfectly timed little pulses that control exactly how much of the AC power gets through to the light bulb. That's how you get that nice, smooth dimming effect. Pretty cool, right?
Okay, now things are about to get a little weird. Let's look at some components that almost seem to bend the rules of physics. They perform these really specific, almost magical jobs. These are basically diodes with superpowers.
So take a look at this graph. This shows how a tunnel diode behaves. What's so bizarre is this middle section right here. As the voltage goes up, the current actually goes down. This is called negative resistance, and it's completely backwards from how things normally work. It's just strange. This happens because of a wild quantum mechanics thing called the tunneling effect. Basically, electrons can just punch right through an energy barrier that they shouldn't be able to cross. And because they can do this, the tunnel diode is unbelievably fast. That weird negative resistance property makes it perfect for creating signals in super high-frequency circuits, like the kind you'd find in microwave equipment.
All right, next up is the varactor diode. Its superpower is that it can act like a variable capacitor.
By changing the voltage you apply to it, you can change its capacitance. The best way to think of it is as an electronic tuning knob, and that's exactly what it's used for, in radios, TVs, and phones, to help tune in and lock on to a specific frequency.
So far, all these components have been living in a dark box, just talking to each other. But the next big challenge is making our circuits interact with the real physical world. So let's take a look at how electronics can actually see by detecting light.
Two main components do this job, the photodiode and the phototransistor. You can see the little arrows in their symbols. That's the universal sign for light comes in here. They look pretty similar, but there is one absolutely crucial difference in how they work. The photodiode is what you'd call a pure detector. Its one and only job is to take light energy, photons, and turn it directly into an electric current. The more light that hits it, the more current it makes. Simple as that. This is the exact sensor used in your smoke detector. It's constantly watching a tiny beam of light, and if smoke particles get in the way and block that beam, the current changes and beep, 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 the alarm goes off.
The phototransistor, on the other hand, is a cool two-in-one device. It's basically a photodiode and a BJT amplifier all squished into one single package. So not only does it detect the light, it immediately amplifies the tiny signal that light creates. This makes it way more sensitive, which is perfect for things like barcode scanners or systems that need to count items zipping by on a conveyor belt.
So, let's step back and put this all together. We've just explored a surprisingly versatile toolkit that gives engineers the power to build, well, pretty much anything you can imagine. Each of these components solves a very specific problem, right? The BJT is like your all-purpose adjustable wrench. The triac is the heavy-duty power controller. The specialist diodes are like a set of precision tweezers for really delicate work. And of course, the photo components are the circuit's eyes, letting it finally see the world around it.
It's really a perfect example of how our deep understanding of fundamental physics leads directly to the technology that shapes every aspect of our lives. From a simple switch to a complex sensor, these little pieces of silicon are the true, unsung heroes. It all leaves you with one final thought, doesn't it? If silicon built our world, what new materials and what new physics will build the world of tomorrow?